we're talking about geometric sequences and signal notation. You'll be able to use the formulas for geometric sequences to find different parts of a geometric sequence, just like how we did for arithmetic. And then you'll also learn about signal notation, its purpose, and how it applies to sequences, and you actually being able to use and write in signal notation. So, in a geometric sequence, it's kind of like the opposite of an arithmetic sequence, where each term can be found by multiplying the previous term by a constant value, r. This one's known as the common ratio. Okay, so you have common difference that's associated with arithmetic, common ratio is associated with geometric. If it doesn't tell you what type it is, but it says find d versus and find r, then you kind of know which one that you're dealing with. You have your set formula of u sub n equals u1 times r raised to the n minus 1, where u sub 1 is still your first term, n is still your number of terms, and u sub n represents the nth term. R, of course, is your common ratio. Question on that. In the setup. Okay? Again, this formula is in your reference booklet, so you do not have to worry about memorizing it, but you do need to know what each term or each variable represents, because that is not in your reference booklet. Okay? So we're going to find the 9th term of the following sequence, and we're also going to find the 12th term of the following sequence. So I'll do one with you, you'll do one on your own, and we are going to use our calculator for this. Now, you won't always use your calculator for a geometric sequence. Just some of them you may have to. Some of them will be nice enough that you don't have to. Okay? So we're going to find the 9th term of the sequence. Can we identify what our common ratio is here? It is 4. Now, if you're wondering, or if you can't easily see it, just like with arithmetic, when you take the second term and subtract it from your first term, you can do the same thing by taking your second term and dividing. So 4 over 1 is indeed 4, 16 over 4 is indeed 4, and then of course 64 over 4 is indeed, 64 over 16 is indeed 4. I was like, that's definitely not 4. Okay? That is also how you would show that something is geometric. So if actually to show that this sequence is geometric or to show that the common ratio is 4, that is what you do. You take every single term and divide them. Every single term. Please make a note that it's every single term. You just cannot take the first and second. Okay? Like in the mark scheme, it says all of them. Okay? So, we're looking for our 9th term, so we're going to plug 9 in for n. Our first term is 1, and our common ratio is 4. And then we raise it to the 9 minus 1. Okay? Now, this is where those powers that I was referring to back in the exponential unit, once like, you want to make sure you know your powers of 3 up to 5, powers of 4 up to 4, et cetera, because when it's a non-calculator, you don't want to sit there and be doing old school. Okay? And then, of course, order of operations. What do you do first? The exponents before you ever multiply it by 1. So you do that 4 to the exponent first, and then you multiply it by the first term. So what is 4 to the 8th power? What is it?
66,000.
Is that right? Okay, so when you multiply that by 1, 65,536. Simple enough. No, that's why I said definitely want to calculate. Now with 4, you should at least know your powers of 4 up to 5 or 6. Those can be very handy in the non-calculator section. Okay? Now I want you guys to find the 12th term of the following sequence. Alright, so hopefully you set it up. You plugged in 12 for n, 7 for your first term, and what was your common ratio? -2. And then you raised it to the 11th power. Now, one thing that I saw in your paper that I just kind of want to make sure that, what's the word called? When you like, try to put this in passing. I don't know. Air management? No, that's not the word. Okay, I saw a couple of you guys put the exponent on the inside, which is fine because that's what the formula was. But I'm afraid that, say this was an even number and you did -2 to the 12th power without putting the parentheses around it, you would end up with a negative number. So do realize that, especially with the negatives, it is that negative number that's raised to the power. Okay? So when you type it in, you want to make sure that it's the calculator knows to do negative 2 times itself 11 times, not 2 times itself 11 times negative. So when you did that and you multiply by 7, don't give me any intermediate numbers. What's the final number? Did you guys get this? Awesome. Easy peasy lemon squeezy. Okay, let's keep it moving. Okay, now here's one without your calculator. Okay? In a geometric sequence, the first term is 864 and the fourth term is 256. We're going to find the common ratio and we're going to do this without your calculator. Now, this right here, as you can see, there is a distance between the two terms that are given to us. It's kind of like the same thing when we're just given two terms in the sequence and we can't really use the two just to divide them to figure out what is the common ratio, okay? But what we can do is something similar to what we did with arithmetic. When we took the two numbers and subtracted them and divided by where they were placed, we can kind of do something similar to that. What we can do is we can take the furthest out term, which is the fourth term. We can take that, and then we can divide it by the closer in term. Okay? And then we can set that equal to I'm just going to go from the beginning because I was going to jump straight to it, but I don't want to confuse anybody. Okay. If we were to set up the general equation using the use of n, u1, r to the whatever, this would be, since we don't know the first, well, we do know the first term, but it doesn't matter. R to the 4 minus 1, is it not? And then this one would be u sub 1, r to the 1 minus 1, correct? Like plugging it into the formula. Well, our u sub 1's cancel out. And then this r to the third would be divided by r to the 0, which is what? Which is what? 1. So then technically this would be 256 over 864 equals r to the third. Now what I was going to say was just subtract 4 and 1 and put that as an exponent with the r, but I didn't want anyone to be like, well, why? But this is why. And that's the work that goes along with it. And it works that way every time. Just subtract where they're placed and then have it be the exponent to your r. So now all you have to do is take the cube root of this number here. Okay? Now knowing your powers, it can be helpful. But if you're like, no, Ms. Anderson, I still can't do this. Can you reduce this fraction? If you're like, okay, I know what number goes in. 2. They're both even numbers. So if you do gotta break it down old school, like keep dividing by 2 till you get a number, then do so. Alright, so what's 256 divided by 2? 128. Okay? And then what's 864 divided by 2? 432. Okay? Can I reduce this? Sure can. 5. Sure can. What's 128 divided by 2? 64. And what is 432 divided by 2? 216. Okay? Can I keep reducing?
Yeah.
Sure can. What number? 2. I can still keep going with 2's. What's 64 divided by 2? 32. And what's 216 divided by 2? 108. Okay? Now, can we keep going? Sure can. Divide by 2. 16 over 54. Can we keep going? Sure can.
Sure can.
What about here? 8 over 27. Can I reduce any more from here? So that equals r to the third. So then from here we can take the cube root. So now the numbers are a little bit smaller and these should be perfect cubes that we know of, right? What's the cube root of 8? And what's the cube root of 27? So our common ratio is 2/3. Okay? Now, will they be this extensive? It's a possibility, but there was a point throughout our simplification process where we could have actually taken the cube root earlier. 64 and 216. What's the cube root of 64? 4. What's the cube root of 216? It's 6. Knowing your powers can help you out there. So that would have been 4/6, which would reduce down to 2/3. Okay? So probably somewhere down the line, if you know your powers, you know, there you go. Questions? Okay. Now this example is going to bring back some memories. It says for a geometric sequence 5, 15, 45, and so on and so forth, the least value of n such that, find the least value of n such that the nth term is greater than 50,000. Okay. So we pretty much know that we're looking for what here? We're looking for n. We're looking for the nth term, okay? Now, we do know that we're looking for a particular value of n such that the nth term has to be greater than 50,000, which means that in our formula of u1 r to the n minus 1, it needs to be greater than 50,000. Is everyone okay? Make sense? All right. So, do we know our first term? What is it? Do we know our common ratio? It's 3, okay? The only thing we don't know is n, okay? And so to find n, we're going to have to go back and use an old concept because, say again, we are going to have to use logs because n are variables in our exponent, and to get it out of the exponent, we need to take logs. But before we go ahead and start logging both sides, we need to divide by 5 first. Good, you all haven't forgotten. Yes, you need to get the exponent and its base by itself. So that's going to be 3 to the n minus 1 is greater than 10,000. This is a calculated problem clearly because, you know, we did a little bit of logs without our calculator, but not to this level. Okay? So now, can we take the log of both sides? Yes, we can. And when we take the log of both sides, that allows us to do what? Bring down that exponent. So this is going to be n minus 1 log of 3 is greater than the log 10,000. So then all we have to do from here is what? Divide by the log of 3 and then add 1. Now, can I say that log of 10,000 over log of 3 is just log of 10,000 over 3? Can I? Refresher from logs? No, you cannot. The only time you can actually divide them is if it was like log of 10,000 minus log of 3. That's when you can divide those numbers, okay? So don't forget about your rules and your laws or properties of logarithms. I think those are properties. Okay? So, because you're doing a log divided by another log. If it was a log minus that log, then you would divide it. What you guys get for this? Are we going to plug it in? So we get 9.38. But you remember what I said last week? So that would have to be, it would have to be 10. It has to be a positive number. Your number of terms has to be a positive number, and it has to be a whole number. So the fact that we got this means that when we're going through our sequence of numbers, inequality showing that you recognize it as greater than this particular value. And you should keep the inequality all the way through until you get to your final answer. All right. This last one, I want to see if you guys can set it up first and then try to solve it before I jump in. All right, so we had to find the value of x. And yes, we set it up so that the second term divided by the first term equals the third term divided by the second. Since this is geometric, that means the common ratios have to be the same. And if we set it up this way, it will allow us to cross multiply and get an equation that we can solve for x. So that's 4x plus 4 squared equals 3x times 7x minus 2. So when you FOIL 4x plus 4, what'd you get? Equals, okay? And so the squares let you know that you have a quadratic, so you want to get everything to one side. So when you subtract everything over, you'll get a 5x squared minus 38x minus 16. And this is factorable, yes? Old school California, multiply 5 to negative 16. That is going to be a negative 80. What were the two numbers that multiply to give you negative 80 that add together to give you a negative 38? 2 and negative 40. Oh, that wasn't too bad. Put a 5x on top and reduce. So that would have been 5x plus 2, x minus 8. So you would have gotten x equals negative 2/5 and x equals 8. And since it's asking for the positive value, it would be 8. Questions? The last thing we're going to talk about is sigma notation. Okay? This was a different day because I did arithmetic geometric all in one day, so that's why there's a whole other set. But you're going to be able to evaluate series using sigma notation and formulas. So, sigma notation, it is that funky looking E that you've probably seen at one point in time in your math life. It basically is the notation used for adding terms of a sequence. Okay? And when you add the terms of a sequence, it gives you a series. So there's a difference between an arithmetic sequence and an arithmetic series. Not too much difference. Instead of commas, they're just pluses. That's really the difference. Okay? So that's what you see with the second bullet. It's U1 plus U2 plus U3, and so on and so forth. Okay? It forms a series. And then the funky looking E, the sigma symbol, represents the sum of all the values. So basically, you're adding your first term to your second term to your third term, et cetera, et cetera. And this is the general makeup that you see right here. Okay? You have your sigma symbol. On the bottom, it will tell you what term to start with, and then the top number tells you what term to end. So in this case, you're adding the sum of the first n terms from 1 up until n of this particular expression. This right here represents the expression in which you're finding the sum of. And so it's pretty straightforward. You're taking that expression that's in the red circle, you're plugging in 1, you're plugging in 2, you're plugging in 3, you're plugging in 4, you're plugging in the numbers all the way up until whatever n is, whatever the top number is, and you just add them together. So, here's an example, right? We have the sum from 1 to 5. So, term 1 up to term 5 of this expression, 6n plus 2. It's non-calculator. A lot of the series ones are probably going to be non-calculated. Okay. And so pretty much all you do is you plug in. You plug in 1. When n equals 1, 6 times 1 plus 2 is 8. Plug in 2. 6 times 2 plus 2, 14. You plug in 3. 6 times 3 plus 2. You plug in 4. 6 times 4 plus 2. Plug in 5. 6 times 5 plus 2. So you take all of those terms and add them up. So 8 is your first term, 14 is your second term, 20 is your third term, 26 is your fourth term, 32 is your fifth term. And then you just add those up together to get the sum of the first 5 terms. All right, so this right here, if it asks you to write out the series, then this line right here with the sum is what you would write. But in this case, we're actually trying to evaluate. We're actually trying to find the sum of this particular series, the first 5 terms, and that equals what? 100. Okay? 100. Question on that? Good? Okay. So like this one, is asking you to write expression as a sum of terms. So basically, you're writing out the terms, and then you're calculating the sum of these terms. I'm gonna let you guys do this one on your own, and then I'll see how you did. All right, so you had to write out the expression as a sum of terms. So that literally means writing out the sums. What was the first term that you got? -2, and then. Okay, so this would have been your answer to A. So then B is just the sum of them, and you got 18. There we go. Simple enough, yeah? Wonderful.
So you're supposed to write the summation and everything equals your answer, not just the answer?
I don't think they'll count off if you didn't write it. So. All right. Now let's evaluate this expression. I'll let you guys do this one as well. Then I'll check it. What you guys get for your answer? 510? Okay. So that should have been 2 to the third, plus 2 to the fourth, plus 2 to the fifth, plus 2 to the sixth, plus 2 to the seventh, plus 2 to the eighth. So that is 8, 16, 32, 64, 128.
The sum is it's 4.
Great.
I got 5. I got 4.
Okay, so okay. Wait, hold on. Okay. Wait a minute. So
That's going from 2 to the 1 to 2 to the 2 and adding those other 2. She didn't start at 3. Yeah, I didn't start at 3. So, oh my.
okay. So wait. Do we get these numbers?
Yes.
Okay. So we're good there. Okay. So wait. So yeah. These are all my patterns. There you go. Let's do today. 256. Okay. Cool. So now we add these. Do we add these?
So the number on the top means the number of terms in the sequence you're doing, right?
No. This is where you start. This is where you stop.
Okay, I thought that was representing the number of the sequence.
Well, technically it is. Technically it is, but we're starting at 3. So this bottom number tells you where you start, and then this number tells you where you stop. So it's 504. Okay. Okay. Yes. All right. So just to make sure we clear this up, the bottom number tells you where you start in the sequence. Like the other ones, yes, we started at 1, but this one in particular, we're starting at 3, and then we're going all the way up to the 8th term. That's where we stop. Okay? Last one. It says to write a series. Write the series using sigma notation. So we have 3, 15, 75, 375, 1875, and 9375. Now with this particular series, do you notice something? Say again? We are multiplying by 5. So really and truly, this is an example of a geometric series. Okay? Because if we just replace the pluses with commas, this would be a geometric means that when we write our sigma notation, the part that follows right here is going to be our rule for this geometric sequence, if it was sequence. Okay? So we're basically going to write the rule. So we need our first term, which is 3, our common ratio of 5, and then it's going to be raised to the n minus 1, where n starts at, let's start at 1, the first term. Yep, is our first term, so think about it, we plugged in 1 minus 1 is 0, 5 to 0 power is 1, 1 times 3 is 3, and it goes all the way up to what? 6. And there we go. So sometimes the expression that you're trying to find the sum of will be an arithmetic one, will be a geometric one. Okay? So you do need to take that also into consideration, especially if it's something not as simple as just going from 1 to 6 or 3 to 8 when you're adding your terms. If it says to go from 1 to 20, you don't want to sit there and write out your 20 terms. You want to kind of recognize that, hey, is this arithmetic or is it geometric? Because if it is one of the two, then what you can really use is the formulas for arithmetic series and geometric series. Okay? But we'll talk about that in our next class. Okay? So